Okay. So exam 1, the scores were really good. But here was the most common mistake on exam 1. And it just had to do with units. So when you did the tensile test, you had units of newtons and meters. And so that gives you compliance units of 1 over pascals. And then problem, what were there, 3? So problem 3 gave you a stress tensor with units of megapascals, and I don't know, half the class, something like that, just multiplied the megapascals to the compliance matrix. You just got to keep in mind what the units are. So you ended up, so if you know, so let's see, so how did you get units that were, you all got units that were too small. 1 over pascals. Oh yeah, right. So your compliance units were too small to use with megapascals, and so you got strain values, even though they're unitless. That doesn't mean that you can multiply any units together to get this unitless value. Okay, so be sure that if you're dealing with pascals in one thing, you get the other one in pascals or megapascals or whatever. Okay, so people were getting strain values on the order of like 1 to the minus, 10 to the minus 10 or something instead of 10 to the minus 4. You're off by a factor of 1,000,000, which is a lot. You can, if you're off by a factor of 1,000,000, your results are not very useful. Anybody have any questions about the exam right now? Yeah. Yeah. Mm-hmm. Yeah. Yeah. So number 2. Yeah, let me just draw it out. So you have 20 megapascals that way. That goes back. That means this goes this way and has a value of 5. And then we have this going down. The coordinate system is this. And so the stress tensor is positive 20 for x. And then that's in the negative z direction of 5. And then 0, negative 10, 0, 0, 0, 0. Yeah, exactly. Okay. Oh, sorry. Okay, we'll fix that. Any other questions? Oh, yeah. So this was probably the second most common problem that people had. If you're using, if you're using a definition of the Young's modulus as the XX normal stress over the XX normal strain, that only works if the x-axis is the loading axis of the member. You know, the loaded axis. And you can do it with other coordinate systems, but okay, so if you're going to use this formula, the x-axis has to be up or down, and it doesn't matter as long as the other two are perpendicular to it. It doesn't matter which you choose. But if you choose up to be your y-axis, because I know we're pretty used to having y-axes up, then the formula for Young's modulus has to be sigma yy over EYY. Because that Young's modulus has to come from the loaded axis. And so sigma XX is, the force was 3,500. And then the area that matters for that, you're always thinking of the cross-sectional area that's perpendicular to that force. So that's the area you want, which is 0.1 times 0.008. And I think you get 4.375 times 10 to the 6 pascals. And then for the strain, it says that the height increases 1.75 times 10 to the minus fifth. Increases means it's positive. So we have positive 1.75 times 10 to the minus fifth divided by the original length, which is 0.25. So notice that here, it already gave you this in terms of the change of length. Okay, so you don't want to do a subtraction with this as one of the two things you're subtracting. The subtraction only comes when you have the length of the side before and the length of the side after. And so you get a strain of positive 7.0 times 10 to the minus fifth. And so Young's modulus is 4.375 times 10 to the 6 pascals over 7.0 times 10 to the minus fifth. And you get it's like 60 something, 60. Anybody have that? 6.25 times 10 to the 10th. And the key thing here that I was just talking about is that the units are pascals. And so you have to make sure that, you know, just be careful with the units. And then for the Poisson's ratio, the side that's initially 0.1 meters decreases. So the side that's initially 0.1 meters is our Z side. So I'll write this as EZZ is equal to, it decreases, so negative 1.50 times 10 to the minus 6 divided by 0.1. These are both units of meters. And what's the value for that? Anybody? Oh, I can do that. I'm not stupid. negative 1.50 times 10 to the minus fifth. And so Poisson's ratio is negative of the strain in the offload direction. So that's a negative 1.5 times 10 to the minus fifth divided by 7.0 times 10 to the minus fifth. The negatives cancel, and I think you get 0.214. And it's always worth remembering that Poisson's ratio always has to be in the range from 0 to 0.5. Anything outside of that doesn't make any physical sense. So you can sort of sanity check your answers on that. Any other questions? Okay. Well, I thought it would be a good idea today to do a truss problem. I'll just write up a truss problem and you guys can work on it together, make sure that you're all, that you all remember how to do that stuff, and we'll turn it into stresses and stuff. So let's say that we have a truss. Well, let's do it with, this is sort of an unusual format for a truss, but let's say that we have one member here, and then a horizontal member here. That has to be a pin joint. And let's say that the length this way is 2 meters. And let's say that this angle is 45 degrees. And that horizontally this distance is 1 meter. And let's put a downward force here of 1,000 newtons. Let's say that each member has a cross-sectional area of 1.0 times 10 to the minus third meters squared. What's the maximum shear stress in each member? Anyone have any questions about the problem setup? Okay, well, work together on it, or if you're working on it by yourself, at least it steps, compare it to the people around you. Ask me questions if you need a hint somewhere or whatever. And when you're done, I'll go through it and make sure you're thinking about it right. All right, so the normal way you would approach any truss, and this is a truss because the members don't have any weight and all the loads are happening at the pin joints. So that means every member in this, each of those two members is a two-force member. So normally you would isolate the whole thing, try to calculate the reactions, and then go to the individual pins. In this, this is as simple as a truss can be, and in this example, you can actually just isolate that pin between the two members and solve everything from that. So a free body diagram of the pin that connects those two looks like this. You have a downward force of 1,000 newtons. You have tension in the member that's at 45 degrees. I'll call that F1. And then tension in the horizontal one, F2. And Newton's second law says, so if we use a coordinate system like this, F2, 0, plus 0.7071 F1 minus 0.7071 F1 plus 0, negative 1,000 is equal to zeros. The y equation says F1 is equal to 1 divided by square root of 2, 1 divided, is that 1414? Okay, and it's negative. That's important. So that means that this member 1 is in compression. And then plug that in to the other equation, and you get F2 is equal to 0.7071 times that. So that's 1,000. Okay, so the situation is this. We have these two members. The first one is in compression. The second one's in tension. I'll call this one member 1 and this one member 2. And now let's just go through it, go through each one. So member 1, and notice that the coordinate system that we used to figure out the loads on each member, we're not tied to those. When we go to calculating the stresses, we can choose any coordinate system we want as long as we're consistent about the loads that were applied. So if I think of the x-axis as being along the long axis of the beam, then the x normal stress is negative 1414.2 divided by the cross-sectional area, just 2 zeros and a 1. And so that is 1.414 negative times 10 to the 6. And so the stress tensor has that in the x position and zeros everywhere else. Normally now, once you have your stress tensor, you would calculate a principal stress tensor, calculate your principal stresses, but in this case, that's already principal. There are no shear stresses. So now we can just say that our T max is 0 minus, the maximum principal stress minus the minimum principal stress divided by 2. 1.414 times 10 to the 6. And so that is positive 7.071 times 10 to the 5th. pascals. So that's the maximum shear stress in the angled member. And now for member 2, anybody have any questions about that one? It's the same procedure for member 2. The XX normal stress is 1,000 divided by 0.001. So that's 1.0 times 10 to the 6 pascals. And so the stress tensor is 1.0 times 10 to the 6, zeros everywhere else. And so the max, and again, that's a principal stress tensor. So the maximum shear stress is the maximum principal stress minus the minimum divided by 2. So that's 5 times 10 to the 5th pascals. And then those are values that you could compare to like the maximum stress you would expect in that material before permanent deformation or whatever you're looking for. Any questions about that? All right, so the next thing we're going to do, start on Friday, but so we're still on members in tension and compression. And we'll do pressure vessels. So the idea is, say that you have this member, this spherical shaped thing that's hollow, and it has a pressure P in on the inside and a pressure acting on the outside, P out. What can we say about stress in the walls? And we'll do a spherical shape like the picture I drew there. And then we'll also do a cylindrical shape. And you can imagine a lot of applications for this stuff. And actually, a lot of biomedical applications with like blood pressure, any kind of lumen where there's fluid going through, you could represent as a spherical thing and calculate the stresses in the walls. I think this is a pretty cool topic, and it's actually not that hard to understand. But this is the last thing we're going to do for pure tension and compression. What? Oh, like a tube, any kind of tube, a hose, you know. Lumen is the opening in the middle. All right, see you on Friday. Scroll up.